that's a stroke of luck. I've completely finished all of my work this week and next week, which is absolutely great. So I have absolutely nothing to do, so I thought I might as well just come on here, knit some socks and chat a bit about Mercury. So we'll do that. I have to be as quiet as possible. I have roommates who I'm not sure what they're doing, so we'll try and be as quiet as possible. I'm using some yarn from my local craft shop. It's just nice grey monotone monochromatic yarn, 4 ply, so good for sock yarn, and I've got a few double pointed needles with the right gauge, and the pattern I'm using is just a very simple basic top down sock pattern with a ribbed cuff. To start off, I'm just going to cast on the sock. I think I'll cast on about 55, 56 stitches, I can't remember. I think it's got to be an even number, yeah. So I'll cast on around 56, and then I'll just do knit 1 purl 1, which is just a simple ribbing for a little while, and then I'll just do some plain knitting. Right, so Mercury, yeah. It's the smallest of all of the principal planets we have, so not including all the dwarf planets like Pluto for obvious reasons. But yeah, it's one of the smallest. It has a radius of about 2,500 kilometers, and interestingly enough, it's also one of the most eccentrically orbited planets. So that means its aphelion, the farthest point from the Sun, is much different to its perihelion, so its closest point to the Sun. So that means its orbit is very much an ellipse rather than a circle, unlike planets like Neptune. A year on Mercury is only around 88 days, which is very small compared to ours, due to its proximity and also its lack of atmosphere. It means that the temperatures on Mercury change quite a lot as well. So you'll have nights which are around, I think, minus 180 degrees Celsius, I think so, and then you'll have days which are up to 450. So that's quite a big temperature change. A year on Mercury is only 88 days, however an actual day on Mercury is 59, so it actually rotates around its axis very, very slowly. We've only had a few spacecraft actually visit Mercury. I think we had Mariner 10, I think. I'll pop the correct one somewhere around the screen. And then we've also had one of the Messenger spacecrafts. I think it was just the Messenger spacecraft that went along and had a look. Of course that changed this year with Bepi Colombo, but since we don't have that much actual data on Mercury, we're not too sure as to what it's made up of, or we don't really have that much information at all. But the things that we know about its structure is that it has a core and a mantle, which is pretty much similar to all the terrestrial planets in the solar system. So that's from Mercury to Mars. So Mercury's core is supposedly a lot larger than the mantle, and it's liquid iron just like ours. Mercury has an extremely weak magnetic field. We know it's a very dense planet, and so what that means is that the core must be quite large compared to the crust and the mantle of Mercury itself. And we know that it has a very weak magnetic field, so that implies that the core itself is most likely liquid iron, a bit similar to our one on Earth, and it's got some sort of dynamo generating that magnetic field, just not a very strong one. Right, I've actually got the cuff mostly done, so yeah, we've got 7 rows of knit 1 purl 1 ribbing, and then 7 rows of stockinette, so nice and balanced, everything's even. We're going to do a Welsh sword heel, well, I will. But what you do basically is you split the stitches in half, and the back half you're going to turn into the heel, and you're going to do a stitch, well I'm going to do a stitch which is a very reinforced one, which is great for the heels like mine, which are shaped a bit weirdly and can sometimes be quite abrasive on a shoe. So yeah, I'm going to do 14 stitches on each side of this stitch marker, so that's where the start of my work is. I'm going to work some very thick stitch for quite a while. I'm not sure how much I'll need to do, but I'll figure it out when I get there. Whilst we're doing that, we're going to also talk a little bit about some of the cooler features of Mercury, so things like its impact basins and also its craters, stuff like that. And then we can also talk a little bit about general relativity for fun. I'm gonna get started on working back and forth, and whilst we're doing that, we'll talk a little bit about Mercury's geographical features. So Mercury's surface is probably one of the richest in terms of basins, craters, cliffs, volcanic remnants, pretty much anything and everything on its surface. It's probably the most richest surface out of all of the principal planets that we have, so not including moons, of course, for quite obvious reasons. And despite that, it's actually it's not really been observed that much. So we had that Mariner 10 flyby quite a few decades ago, and then we had Messenger as well, which is slightly more recent, I think. Yeah, so we haven't actually had that much look at Mercury close up, which is kind of a shame. But then again, we've got things like Bepi Colombo and future spacecraft, which will hopefully bridge that lack of data and lack of information that we have about Mercury. The evidence that we have for these features suggests that they were formed roughly when Mercury itself was formed, or at least when it was extremely young and a little bit more active. A lot of volcanoes that we see, or what were volcanoes, I guess, and a lot of the geographical features are very inactive on Mercury, so it suggests that these things were formed when Mercury was quite young. One of the most popular ones that people who look at Mercury quite a lot, well, don't look at it directly, but look into Mercury, ones that they know is Caloris Basin. So this is a ginormous impact basin that's on Mercury, and within it actually it contains 9 volcanic vents that are all sort of interacting or intersecting and mingling with each other. It's fair to say that Mercury's surface is quite similar to the Moon's, although I'd probably argue that Mercury itself is way more unique than the Moon in terms that its internal structure has sort of led to a much wider array of geographical features. So I really do think Mercury is just that much more unique. Unpopular opinion, I guess. But looking at Mercury itself from the ground is actually quite difficult due to its proximity to the Sun, and we'll get into that a little bit later, but I also want to focus a little bit more on the geographical features first. Caloris Planitia is one of my favourites. It kind of has a little bit of everything where it is, and it even has evidence that there was once volcanic activity on Mercury, so hinting towards Mercury being once a very active planet. It's an incredibly large impact basin, basically. It's about 1,500 kilometres wide, so it actually takes up quite a large portion of Mercury's surface compared to all the other features on Mercury, and it appears to have been smoothed out by lava, which is quite interesting because it means that there was volcanic activity, there was fresh lava, which is not something that we see on Mercury nowadays. But yeah, it does hint towards a very active Mercury in its past, which is pretty cool. So we don't actually know quite well where this impact basin sort of stops. Some parts of it are actually surrounded by mountains, which are about 2 kilometers high on average, which is really cool. But there we go. We don't actually know where the actual impact basin ends. It's been smoothed out quite a lot. Looking away from impact basins and craters and stuff like that, one of the more unique features that you see on Mercury, which, yeah, they're rather distinct, are called extension faults. They're these spidery little troughs that sort of stretch out around the planet. On Earth, these are formed by the stretching of the crust, very rapid stretching, of course. So it's kind of similar to how you can get stretch marks on your skin. So one of the most intriguing cases of these extension faults is actually within Caloris Planitia again. The image that I'll show you, I'll try and pop it somewhere on the screen, is Pantheon Fossae. So that's the name given to the spidery troughs that are within this Caloris basin. Caloris Planitia. This image is actually quite a crazy one because we've actually got craters, one of which is called Apollodorus. You can see it in the picture itself. And one of the interesting things about Mercury's extension faults is that we think they're pretty much the same in terms of their cause and sort of creation as compared to Earth, but we're still not quite sure as to how these ones have actually formed. Right, finish the heel. There it is. Can you see it's really ribbed like that? So it's actually quite a much thicker piece of fabric than just some plain normal stockinette right there. So I've actually done, is it 30 actual rows of a sordal heel, so that's 15 front, 15 back rows, which produce this fabric. So this is going to cover bottom of the heel, and now that we've done that, we're going to do something a little bit trickier, and that's actually getting this top part to slowly build it down to match the bottom part, all while actually continuing on the sock, which I'm pretty used to. I just can't remember how to do it, but I think we can get there.
2,000 years later.
I've just picked up loads of stitches from the heel. Don't know if the video actually went through. My phone's being really annoying, but anyway, yeah, I've just made the heel. I picked up a couple stitches along the side of the heels and then basically connected every single every single stitch that we had as I was making the heel. So now everything's sort of looking kind of sock-like. So what we've got to do is, before we actually started this heel, we just had the stitches at the top and also these stitches at the heel split into two very evenly, like I said before. But now we've made a long heel, so we've actually got extra stitches along the sides of the heel that we've picked up. And what we're going to do now is, as we're working the rounds nice and slowly, every other row, we're just going to decrease one stitch on each side, and then after about 15 rows, I'm going to decrease, I think, for every other row 15 times, and then that should get rid of all of those extra stitches and just make the tube just decrease slowly into the actual foot itself. All the planets that in this solar system, and actually pretty much all orbits within the actual universe itself, are to some extent eccentric. So nothing is a perfect circle, really, ever. So everything's going to be slightly elliptical. Mercury itself being probably one of the most notably elliptical orbits, because it's just a very squashed ellipse. I mean, no other way to describe it, really. So if you imagine the sun in the centre, and then you can imagine Mercury's sort of elliptical orbit. One thing that Newtonian mechanics doesn't really get is precession. So what we'd expect with Newtonian mechanics is, whilst Mercury's aphelion, so its furthest point, and its perihelion, so its closest point to the sun, might change a little bit due to maybe the gravitational tugs of other planets like Jupiter, for example, the actual position of the orbit should pretty much be the same throughout the entirety of time and space itself. But in reality, that's not true. And what we see, if you go back to that mental image of Mercury's elliptical orbit, a little ellipse, is that we get the actual orbit to shift very slightly over the course of many, many Mercurian years. And that's something that Newtonian mechanics doesn't actually consider very well. For a long time, I think the problem was first noted in around 1859 by a French, I think it was a French physicist, Leverrier, yeah, that was his name. He first noted the problem that Mercury's orbit doesn't actually line up with Newtonian mechanics really well at all. So he first noted the problem, and the first hypothesis as to what the problem was that there was an extra planet between the sun and between Mercury that we had just never ever seen at all. Which, thinking about it now, that's kind of a stupid hypothesis. I know I'm not meant to say stuff like that in physics, but you know, it really. So they named this planet Vulcan, and loads of astronomers went out to search for it, and surprisingly nobody actually came up with anything solid. After not being able to discover it, the attention turned towards the mechanics and the physics itself. And for a while people thought that perhaps the actual physics behind orbits and orbital mechanics was incorrect, which that idea itself is pretty much spot on. So along came general relativity and Einstein quite a while later, and using general relativity, the predicted precession, so that orbital shift of Mercury, pretty much matched the observed precession that we saw, which is fantastic. In fact, Mercury's un-Newtonian precession has pretty much been noted as one of the best pieces of evidence towards general relativity, which is kind of wild because general relativity and a lot of these large cosmological concepts are things that we apply to deep space, so ginormous objects like quasars and black holes and stuff like that. But it's kind of neat that we have a little piece of relativistic proof just within our solar system with the tiniest planet that we actually have, which I think is absolutely adorable. So let's actually finish off this row. I'll see you in a little bit. I think the final thing I want to touch upon is Mercury's magnetic field. We spend quite a lot of time, money and effort into magnetic fields of other planets such as Jupiter and Saturn, and actually it's kind of paid off. We've got some really good breakthroughs, especially this year with, I think it was Jupiter's aurorae and how its magnetic field interacts with its moons, which was quite amazing. And actually I saw one of my professors was cited in one of the posts that I think it was ESA that had made the post, so I was actually really excited to read about that. But we don't actually know that much about Mercury's magnetic field, which is kind of a shame because despite it being quite a small field in itself, I think it's only about 1% Earth's actual magnetic field strength. It's actually quite a substantial one for quite a few reasons. First of all, it actually is strong enough to actually deflect solar wind from the sun, obviously, and that's quite significant. So it actually creates its own magnetosphere, which you don't actually get all that often, to be honest. You can get twisted bundles of magnetic field. So if you remember from school, you'd see magnetic field lines being drawn as just lines similar to on a bar magnet. So you'd get bunches of these magnetic field lines getting twisted and sort of tangled, and they can open up areas where the sun's solar rays and the solar wind can directly hit Mercury. We actually get this on Earth, however, we only get it maybe 10 times less than Mercury, so it's really, really frequent on Mercury. And this is actually quite an important thing to think about because our technology is kind of vulnerable to the sun's solar wind and a lot of coronal mass ejections, these kinds of solar phenomenon. And so if we could sort of study on a planet that has these occurrences very frequently, we could definitely learn a lot more about how the solar wind works, how we can even better our own technology to sort of just better humanity. And it's kind of good that we've got Bepi Colombo very recently, that's going to go along and study this kind of stuff. And I mentioned Bepi Colombo quite a lot because I myself am actually taught by one of the scientists that built components for Bepi Colombo. One of my lecturers, Susie Imber, you might know her from Do You Have What It Takes to Be an Astronaut, one of the really cool TV shows that I used to watch. Yeah, she's extremely enthusiastic about Mercury's magnetic field for obvious reasons. She's the one that's going to be actually measuring and collecting data on Mercury, and so of course I kind of have to sort of talk about it a little bit at least. Nobody told me that I had forgotten to do the heel, which is very unfortunate. See, I did the heel gusset over here, but you also need to do the heel turn, which is this curved bit. And I've unfortunately forgot to do that, so I ripped out loads of stuff and then I put it back in, which is great, but now I'm just extremely tired of knitting and I'm going to take a break, and that will be where I end the video. So from here onwards, it's actually quite simple to finish off the rest of this sock because you've done all of the complex increase, decrease, stitch change, whatever, all you have to do now is just knit in the round like a tube, no increases, no decreases, until you get to the toes. And then all you do is you start decreasing at the sides every other row, I think, at both sides. So that's really simple. And then once you get to the end, you just cast off everything and just make a little, tie it all together, and you're done for one sock at least. So yeah, that's pretty much where I'm going to end it. It's good talking about Mercury. I really think we should look into that planet a little bit more. It's got a lot of interesting stuff that's just waiting to be discovered. That concludes today's video. I think I'll just head out. Good knitting.